Good morning. So people are gathering. Soon we can start, or we can start right now. I will ask my colleague Beruta to start recording. Later on, we will publish our webinar on our page, and you will be able to come back, read, listen. Okay, so today we will have a webinar about differential pressure controllers. I'm proposing to write questions to the chat, and later on, after we will accomplish our training, we will be able to go through the questions, to read them, to answer them. I'm asking to do so because some questions are popping up in the middle of a seminar, and actually the answers might come in a few slides later on. So we have quite extended overview of a process. Therefore, it would be good just to go through the topic and later on to check and answer questions. So probably you know how to use it, how to write, how to type questions in the chat mode. And today we're having seminar in English. Tomorrow we will have it in Russian. So we can start our webinar. We'll speak about differential pressure controllers and phenomena. How does it go? So we are starting from the questions. There are questions which are arising during designing and during maintaining of substation. There are questions about district heating network. How does it work? I had included extra topic about valve authority phenomena. Then after that, we will switch to differential pressure controller itself. We'll have an overview of differential pressure and flow controllers. And then we will switch to sizing, ordering, installation. Questions during phase of design of substation. Some can ask, what is differential pressure regulator? Some may ask, who needs it at all? Maybe I shouldn't include it because it's obsolete, expensive, or whatsoever. Then if we are ready to size it, then we'll have questions how to choose. Natural questions are coming, where to put it, which pipeline to be chosen, supply or return. Might be someone will ask one or more controllers in the substation, because we have quite often not only heating or hot water, maybe ventilation, or something else. Then we might ask ourselves what data should be included in the project so someone can deliver relevant component. Questions which are not popping up for designers, but they are popping up to maintaining companies or district heating utilities. Why do residents complain that it is too cold or too hot? Why is not enough of differential pressure in the substation? Why does the temperature of heating and domestic hot water fluctuate or oscillate, you may say so? Why return temperatures to district heating utilities are high? How to reduce heat loss in the networks? How to reduce the energy consumption of network pumps? Why do we hear noise in the control valves? Why did the hot water heat exchanger leaks? I have a technical issue. Slides are not turning. What we have to consider that design and actual energy are changing with the time, with the period of the year. The demand may change dramatically. When we are sizing differential pressure controllers, or we may say so, all the heating controls, we normally are aiming at the maximum capacity, which is taking quite short period of complete heating season. Here probably this part is just consumption for the domestic hot water. Even during the day, energy consumption is changing, especially when we speak about domestic hot water. Let's look in the consumption scenario. Suddenly consumption increased. Why it can happen? Because switch from saving to comfort mode had happened. We are facing underflow at remote consumers. We have a real life scenario here. A small town, relatively small, having about 500 consumers or 500 stations, was set by district heating utility to scenario that energy saving is taking place during nighttime, and suddenly complete town simultaneously had called for the heat. For example, it had happened at 6 o'clock in the morning. What district heating utility faced? They faced that remote consumers somewhere far away are not receiving energy because differential pressure controllers were not installed. And as we are sizing control equipment, normally we are sizing it with some kind of safety, with extra margin. We're not capable to size goats precisely, and we are afraid that something might happen and we will need an extra. So it had happened that complete city was struggling with energy at remote consumers, and only after half of a day, when the closely to district heating utility situated consumers were satisfied with energy. Naturally, that is leading to a return temperature increase. Network pumps are working at max speed and underflows were still present. Of course, it might also lead to complaints about unstable hot water temperature. And when we switch to consumption decrease scenario, we also might face complaints about unstable hot water temperature. So why all that is happening? Let's presume that district heating utility is supplying energy with a pump which is keeping constant differential pressure inside district heating utility. Then when we have 100% flow, we have pressure loss in the pipes, and only this very part is used for sizing of differential pressure controllers. Therefore, designers should receive data from district heating utility about minimum differential pressure conditions in the station. Later on, designer will have to chop the differential pressure to different components. What happens when consumption is decreasing? 50% flow. Naturally, pressure losses in the pipeline are decreasing to 1/4 of previous value, and we have a rise of differential pressure in the station. So we see that at 100% flow, we have delta P in the station 2 bars, and when we go to 50% flow, differential pressure in the station is increasing to 5 bars. So 5 minus 2, we have excess of 3 bars. Differential pressure is still maintained at district heating utility on constant level, but the remote consumers are suddenly receiving larger differential pressure. So motorized control valve will have to close to compensate on that increase. And as I told you recently, we might face pressure drop even larger because of too large flow. I just express it like 100 plus. So remote consumers might face a situation where they have lower differential pressure compared to the one which was at the designing stage. We can illustrate how things are happening with speed controlled pump, where we have system resistance, which is built from several components. Like, for example, here we have delta P for control valve. Yellow will be pressure drop on heat exchanger, blue one, some other components, green one, pipe, a line component, so yeah, a pressure drop in the pipes. So actually, when our consumption is decreasing, pressure drop, which a control valve has to eliminate, is increasing. So we can proceed further on. If differential pressure is changing across the motorized control valve, and just to simplify it, we mean that controlling device, ECL, had not yet sent a signal to compensate on pressure increase. So during that very moment, the flow through the valve is increasing. And let's presume that delta P on motorized control valve is much larger than before. From 1 bar, it jumped to 3 bars, for example. We can presume that flow suddenly increased almost twice. And naturally, building is not capable to take all that energy. So here we have a high return temperature, which might be compensated by its sensor. But all these purges and sudden movements are quite fast. Yes, with a time, controller will compensate on that. But motorized valve will have lots of things to do. Meaning, increase of differential pressure controller is influencing temperature for sure. So here we are coming to the topic. The differential pressure controlling valve is the one which is helping to keep constant delta P across the motorized control valve to keep stable conditions. And what is done by differential pressure control valve? Control valve, motorized control valve is opening and closing only on the temperature change demand, and it's not disturbed by pressure fluctuation. The wear and tear or movement of a valve is saved, so it might last longer. So influences on fluctuation of changes is decreased to a minimum. Yes, lifetime increased, overflows are eliminated, so we have kind of balance in the network. And pumping cost for sure can be saved, and return temperature can be decreased, and heat losses can be reduced. By this, we can say that we are saving also on CO2 because we're consuming less power. We're not wasting it. And complaints on poor control are minimized. That's an example from Sweden. You can read about that if we are controlling in a proper way return temperature, and if we are capable to reduce it, we can save on money. I will skip this slide. You will be able to read it later on, but just general overview will be that reducing return temperature by proper control, we are saving money. And here some answers are coming. Who needs it? Maybe not to design it at all. I can illustrate that some countries might have regulations where differential pressure controllers should be used only at some certain conditions when the differential pressure in the house inlet is large enough, for example, 4 bars and more. I would say that it is needed for balancing of the customers and consumers. And doesn't matter the differential pressure you have in the station. I would stress that as smaller differential pressure you have, as more difficult it is to control consumers. So I would advise to install differential pressure controllers in any case. Why do residents complain that it is too cold or too hot? Network is not balanced. Overflows, underflows. Yeah, sorry. Why is it not enough of differential pressure in the station? Energy is used at other stations. Why return temperatures are high? Overflow. There are different reasons too, but one of them is overflow. How to reduce heat loss? How to reduce energy consumption of the network pumps? Balance network. Here is a very nice example about not balanced and balanced networks. As you can see, consumers situated close to a district heating utility are hot, are satisfied, and you can see that return temperature is also high here. That happens because of short circuit, and the most remote consumers far away, they're not receiving energy. What we do, we're balancing network with a differential pressure controllers. We're setting them right, so everybody is receiving energy. And return temperature to district heating utility is on the good level. Otherwise, if we're not doing so, so imagine yourself that you are living somewhere far away, and what can you do in order to get energy? It's to buy on your own money for some controller to fix flow at the station which is situated close to district heating utility. Sounds quite ridiculous. Here I'm jumping to what is happening in the station. I would give an example about static characteristics of a heat exchanger. How does it work? This figure, these lines have different values, and they depend on temperatures. So they might be different ones. And when we are speaking about domestic hot water, normally we have bended curve of heat exchanger. Means that if we are having 100 flow, we are having 100 energy. But if we are having 50 flow, we are having 70 plus power. So the most difficult point for controlling in the station is domestic hot water, and especially low flow, where small change in the flow gives high power capacity, we may say so. So valve authority phenomena is illustrated by these charts, where heat exchanger has his power relation to flow curve. Then manufacturers are producing valves which normally have a opposite control curve. And our goal is to add these two guys together and to receive a linear energy control capability or feature. So let's presume we're opening 75%, we're getting 25% of the flow. So 25% of the flow gives 75% of power. So on the end of the day, we have a nice control capacity. And valve authority is understood from relation to differential pressure across the motorized control valve when it's fully opened, divided by differential pressure which is available when the valve is closing, should result in the relation at least above 0.5. Mean that if differential pressure across the valve is 50, so it is desirable that differential pressure, which might affect or be present across the valve, should not be larger than twice larger than, for example, 50 kilopascals or 0.5 bar. So here we should expect something not larger than 100 kilopascals. So here I will illustrate with the situation in the station. What do we have in the stations? Yes, we do have some line components like strainers, energy meters, pipes, some balancing valves or something else, motorized control valve, heat exchanger. So idea is that motorized control valve should have a resistance which is not smaller than sum of all other guys. So if we have 100 parts of pressure in the house inlet, so control valve should consume at least 50. You can remember it like who owns or who rules in the company, who is handling the business. The one who has a 50 plus shares. So if control valve has above 50% of the shares, it can control something. And if control valve will be sized with a low part of the shares, so it will just jump around and have limited capability to control. As I explained earlier, with the decrease of the flow, the part of differential pressure for the line components and for the rest of the guys is decreasing, and control valve has to compensate. And it's Even worse when we are reaching almost zero flow. Control valve have to take over all the pressure which is situated in the station. So what happens if the control characteristic is distorted? Heat exchanger is still performing as it was, but control valve characteristic is distorted. And when we will add these two guys together, we will receive something bad. As you can see, valve opened just 25% and we have huge overflow. So authority is distorted and control is poor. Therefore, we can expect jumping and oscillation on low loads. Now, I jumped too fast. Idea is the differential pressure control is maintaining differential pressure, so control valve can operate very well. As you can see, in this scenario, we are controlling differential pressure for these two guys. So our control authority is 0.7, which is quite okay. But we have scenarios where some is deciding the differential pressure controller should be installed far away from the station, somewhere almost on the inlet of a station. And then we have a different scenario. We have to include in the range of differential pressure controller all the guys, all the components, because otherwise we will have no flow. So we have to add all these meters, exchangers, balancing valves, and we are ruining control characteristics. That is a wrong way to do so. But somebody is doing. So consider this scenario as a wrong one. What can be done? Impulse tube should be sent somewhere as close to the heat exchanger as possible, or even the best scenario would be that impulse tube would be connected just behind the valve. I know that these schemes will be used and you will still continue using that kind. What can I ask? Whether I can propose that do so that the pressure drop or portion of the pressure drop on the valve is as big as possible. It should be larger than sum of all these guys. Of course, there are limits. We will come to that later on. I just draw the scenarios which are happening. The red one, where we have no differential pressure control, probably will be the worst one. The one yellow, like a street light, will probably contain some components, which is sometimes okay. And the best scenario is when we do have a differential pressure controlled across the valve. Of course, that is leading to single pressure controller. Now we can jump to the construction of differential pressure controller and how does it work? Actually, differential pressure controller is something like a scale where you are measuring two things. One spring inside of a pressure controller is responsible for the range you would like to set with differential pressure controller. For example, from 0.2 to 1 bar, meaning that you would like to be capable to set differential pressure here from 0.2 to 1. And what are you doing? You are doing it with set point selection spring. Actually, that spring is the one where you are setting your differential pressure controller, and some tiny spring, which is not visible here, is sitting inside. So when you are setting your desired pressure, controller is measuring pressures, and it stabilizes, or at least it is thinking that it is keeping balance. Pressure points which might be understood. Here we have pressure in the supply. After heat exchanger, we will have some lower pressure because of resistance of heat exchanger. We will have some intermediate pressure, and here we have return pressure. Question about where to install differential pressure controller. Should it be on the return or should it be on the supply line? If you will do so, for example, you will install differential pressure control valve on return, then your system will be subjected to the pressure which is almost like in the supply line. Yeah, okay, minus some resistance of the valve or what. And pressure here in front of a differential pressure controller will be high. Where do we do it? In some applications where we need to push pressure up, just to keep a static pressure high enough to prevent air separation from the water. And many other applications, so quite often, what do? We install differential pressure controller on the supply line. Then pressure after pressure controller is smaller. It's just throttled. So to wrap up, we may say so that that application is more stable maybe in many cases. And we are quite often installing differential pressure controllers on the supply line. And as you can see, there are two impulse tubes normally. One is marked with plus mark, another with minus, plus higher, minus smaller. You shouldn't disconnect these pressure lines during pressure tests, so controllers should be subjected to more or less same pressure during pressure test. Otherwise, you may destroy controller. Overview of differential pressure controllers. We'll speak about AVP, or automatic valve pressure, we may say so, and AFP plus VFG. There are other components like smaller differential pressure controllers and large ones, pilot controlled ones, which are used quite seldom, so that needs extra discussion. But these large control valves might be used in the applications with pipes of DN 200, 250. We have also differential pressure control with max flow limitation. We have flow control valves, which are working like a flow limiters. So you're just setting maximum flow and your station won't get more. Actually, you can do almost the same function with differential pressure controller while setting it. We'll talk about it later a little bit. We have relief controllers, which are like bypass valves dedicated to the applications where you need to open the loop when something is closing and pressure is rising. We have pressure reduction controllers just to reduce pressure from high to small. We have them for steam too. We have differential pressure control and flow limiter combined in one construction with two membranes. Quite sophisticated automatic feature. And the last ones, we have pressure independent control valves with flow limitation function and motorized control valves. Let's see how pressure controllers are constructed. They are constructed from the valve, which has an insert inside. We have a pressure control membrane with a setting handle, Some controllers might be for fixed setting without this handle. A unique feature of our products is that we have safety valve, which is opening on differential pressure increase above 2.5 or 3 bars. So if you are pressing larger pressure to the plus side, small safety valve will open and let water go through and will protect membrane. Larger controllers are constructed almost with the same scenario: valve, setting element. What should be reminded that these valves are made so that the sealing is in the membrane. So when you are installing your system and when you are not attaching membrane, the valve is open to atmosphere, so water can go out. Please consider it during installation. When we are sizing things, we have to know that we will have to dedicate pressure to each and every component. Here probably I have to address one question to the sizing of a flow if we are sizing differential pressure controllers to several components. Our practice from international and national projects is that if a differential pressure controller will be selected only one or single to several circuits, there are two scenarios we were using often. We were sizing flow or water quantity based on 100% heating, 100% ventilation, and 70 parts of domestic hot water. That's one scenario. Another scenario was that we were sizing differential pressure controller valve size based on the largest flow which might happen, meaning if domestic hot water flow during summertime will be larger, we will pick up that water flow. On the other hand, we are now facing the designers sizing flow based on so-called breakpoint when outdoor temperature is close to zero and when district heating temperature is fixed to some certain value, for example 70 degrees, then we may say so that the flow will be largest. We are getting into a risk to oversize control valve because domestic hot water control valve might be big enough and might be incapable to control water during circulation demand, and the valve, motorized control valve, might start oscillating, what might be amplified by differential pressure controller. If you are sizing stations with a mixing loop, so you are just not including differential pressure to this very loop into pressure drop calculation, because pump has to circulate water inside of the building. How do we size? We are selecting flow, divide by delta P. Normally, we are splitting pressures across the components, and as was said, we know how much pressure we will consume with the heat exchanger, with the heat meter, some other components. Then we are trying to put it 50-50 or something to control valve and differential pressure controller. It's a good practice to dedicate at least 0.3 bar to differential pressure controller because it needs some pressure to operate. The limits, they are related to cavitation. Water might boil in the differential pressure controller. So what do? You are taking pressure in front of the control valve. You are subtracting absolute saturation pressure. For example, you have 100. So you are subtracting 1 point something bars from pressure in front of the valve. You're multiplying by Z factor, which is present in the data sheets of Danfoss. As smaller valve, as larger it is. After you've selected your KVS value, you are checking the valve opening. You're dividing KV by KVS, and that relation should be above 30%. So control valve or differential pressure control valve should be capable to control the processes. It shouldn't be sized too big. You might check flow speed in the valve. Normal condition to the control valves would be about 3.5 meters per second. Limit for the erosion is somewhere about 5 meters per second. That's normally not present in the data sheets because that's quite tricky, and it depends on construction of the valves. Good hint to use heat selector from Danfoss, which is available online, where you can check valve opening, valve speed. Yeah. Range selection, what should be included in the design. There are different ranges for differential pressure controllers, and manufacturers are using them with the purpose to have a precise control. Let's presume that your control valve has a pressure drop of 50 kilopascals or something, then you are choosing differential pressure controller with this very range. Don't do mistake. Don't include pressure control valve with very large range, because it will have an error. And differential pressure controllers are proportional valves, and they are acting with some error, which is called P range or proportional deviation. When you set the valve on 100%, and with a decrease of the flow, you will face increase of pressure across the valve. Here is an example of 3 cases, 1 to 3. For example, you need a setting of 1 bar, and you are free to choose among all these 3 controllers. As an example, you might predict that industry standard for some controllers might be about 20% from the maximum set point. It depends, of course. P-band depends on many things. I will not go deep into it, but for the very rough and brief estimation, without looking into a producer, you might expect that differential pressure will increase. So if you will choose this one large controller capable to control from 1 to 6 bars, it will give you P-band of 1.2 bars. So you set 1 bar on almost low flow, you will get 1.2 bar plus. So you will get 2.2 bars of pressure. So that's an error as well. So you should include a pressure controller which is available from the producers and as close as it could be. Ordering, yeah, what do? You are selecting, for example, with Danfoss AVP, we have 1 impulse tube already inside controller. Some models need 2 impulse tubes. You're selecting installation place, selecting range, yeah, and you have Danfoss code number, and here you go. For the impulse tube, here in Lithuania, we use this special tube, 6929, which is capable to damp oscillations, because otherwise you can use ordinary 60 millimeter copper tube. Fitting, one fitting is provided with a differential pressure controller where you can connect it to the body of it, and another end of a differential pressure controller impulse tube should be connected to the process, to the pipe. With a large pressure controllers, you are selecting the valve, selecting the actuator, selecting impulse tube, which is larger one. Installation. Normally happens the differential pressure controller is installed in wrong position. For example, if you're installing it in the supply line, you shouldn't install it with a membrane facing up, because you will get here gathering inside the membrane, and pressure controller will control with a large oscillation and large fluctuation. So there are some limits. Impulse tube should be connected to the pipeline top or side, never bottom, because it will collect dirt. When you're setting pressure controller, you might look into the pressure indicators or manometers and set the pressure you need to be controlled. Some say that you have to open control valve to 50% and then set your value. Some will say that if you would like to limit your flow, you're opening all the valves in the station you have. Then you are looking at the energy meter, which is situated somewhere at the inlet, and you are setting pressure controller to desired value. Some might include control valve, not control, but shut-off valve on impulse tube. That should be considered to be open during pressure tests. You can seal the setting, so no one is changing it, because one of the issues would be that differential pressure setting is manipulated by maintaining companies on the will. So somebody is coming and turning and twisting and setting whatever he wants. It would be good practice to seal them. With a large control valves, I should also consider temperatures, and DN1580 valves can be installed in different positions, but larger ones not, because they can, with the time, destroy the ceilings because of heavy weight of I would say because of moving inside of the valve, but not heavy weight. So it comes with big valves operating like a saw inside, and they can destroy themselves. So big valves would be good to be installed so that membrane is facing down. Also, you can set them and seal them. So I came to the end of a discussion or presentation. We may stop recording